Hey everyone, welcome back to another TxePrep interesting integrals video. And in this video, we're going to try finding the integral of I to the power of x. And you may be wondering how we're going to find the integral of something with such a weird and unexpected base. But there's a rule of thumb. Whenever we have a weird base for an exponential function, we always want to try converting it to e to the power of x, because e to the power of x is our best friend. So let's try rewriting this in terms of e to the power of x, and we do it like so. We change this to the integral of e to the ln of I to the power of x dx. And the reason why I did that is because e and ln of I cancel out to just I. Because like e to the power of ln of any number just becomes that same number inside of the ln. So this is essentially the same thing as I to the power of x. And we can rewrite this as e to the power of x ln of I. And the reason we can do that is simply just because of basic exponent rules. And now all we have to do is try integrating this. And we notice that ln of I over here is simply just a constant, which means we can apply some pretty basic rules to this. So suppose we have the integral of e to the power of some constant a times x dx. We can rewrite that as e to the ax divided by the same constant a. So we can just apply this over here, and that leaves us with e to the x ln of I divided by ln of I. And we notice that e to the x ln of I is literally the same thing as I to the power of x. So I'm just going to rewrite this as 1 over ln of I times I to the power of x. And obviously, we need a plus c. So, sounds simple enough, but really the monster here is finding out what ln of I is. And in order to do that, we can use Euler's formula. But ln of I is basically just asking us to find e to the power of some number z where it's equal to I. And as I mentioned before, we can use Euler's formula to do that. So Euler's formula states that e to the power of some I times phi is equal to cosine of phi of, not theta, of phi plus I sine of phi. And basically what we're going to do is just find some phi such that this is equal to I. And the way we can do that is by trying to make cosine of phi 0 and sine of phi 1, because then we'll just have an I remaining. And the obvious choice for choosing a phi to do this is when phi is equal to pi over 2, because cosine of pi over 2 is simply just 0, and plus I sine of pi over 2 is simply just 1, and this leaves us with 1. And this makes sense if you look at a unit circle. So I'm going to draw a unit circle over here. This is my really bad circle. But basically when we have an angle of pi over 2, we see that our coordinate over here is simply just going to be I. And that's exactly what we got from the formula. And I might try proving Euler's formula in a later different video. So now that we figured out that phi is equal to pi over 2, we realize that ln of I is equal to z, and obviously z is equal to I times pi over 2. I times pi over 2. And now we can simply just plug that back in over here. So what we can do now is I'm going to erase all this over here. So we realize that this is going to be the same thing as 1 over I pi over 2 times I to the power of x. And I just don't like i's in the denominator. I want to go above. So what we can do is multiply this side by I and the numerator and the denominator by I. So simply just multiplying by 1, which is completely legal. And that becomes I times negative pi over 2. And we can bring the 2 to the top because that's how fractions work. So this simply just becomes 2i, negative 2i, over pi times I to the power of x. And obviously you need a plus c over here. And that's going to be our final answer. And obviously you could simplify it more. For example, instead of putting it like negative 2i, you can just make it I to the power of x plus 1. And there we go. That is our final answer for the integral of I to the power of x.